po.
Good afternoon, class.
Afternoon, Doc.
Afternoon, Doc.
Are you all in?
Afternoon, Doc.
Afternoon, Doc.
Afternoon, Doc.
Okay, our topic this afternoon is about free radicals. Now, tomorrow, we do not have a class. Diba?
Yes, Doc.
Little landing. Okay, so let's start. Free radicals and antioxidant nutrients. Okay, take note. Free radicals are formed in the body under normal conditions. So every day you're forming free radicals. That cannot be, that cannot be avoided because we are dependent on oxygen. And oxygen is an oxidant. Okay. So free radicals are formed and they can cause damage to nucleic acids. Very, very important, nucleic acids. That don't mean your DNA, your RNA, your tRNA, your messenger RNAs will be affected. Now, not only your nucleic acids are affected, also proteins and lipids in the cell membrane. So what's going to happen if the cell membrane components, because it's made up of lipids and proteins, and free radicals attack them, the cell membrane becomes weakened, or some of the functions of the cell membranes cannot be performed. As well as your plasma lipoproteins. Your plasma lipoproteins, you have your chylomicrons, you have your VLDL, you have your LDL and HDL. And these lipoproteins have very, very important and delicate function. So if their functioning can be disturbed by free radicals, then these lipoproteins will not be working as they should. Now, as a result of that, it can cause cancer, atherosclerosis, coronary artery disease, and autoimmune diseases. Autoimmune diseases. Okay. Now you have protective antioxidant, and this includes vitamins and very important metal selenium. So you have vitamin C for environment that is aqueous in solution, because vitamin C is water soluble. And you have vitamin E and the B carotenes, which works well on a lipid environment or fatty or oily environment. Now, beta carotene, you know, it is the precursor of your vitamin A. Okay. So there are other carotenoids as well as polyphenols coming from plant foods. Now, many of us are taking dietary supplements of one or more antioxidant nutrients. However, there have been studies whether these dietary supplements are helpful or not. So the study shows little benefit of antioxidant supplements are seen, except in people who are deficient of those antioxidants. For example, there have been many trials of vitamin A from beta carotene and vitamin E. So increased supplementation of these vitamins shows an increased mortality among those taking the supplements. Paradoxical, yes? No? We know that it helps us, but an increase of this beta carotene and vitamin E shows an increase also in mortality. Now, I will talk about that as we go along. All right. Now, free radicals are self-perpetuating chain reactions. Now, you should remember that these free radicals have an unpaired electron. Unpaired electron. So, they are in search of an electron so that they can be stabilized. Because if you have an unpaired electron, the molecule is unstable. So they would like to get an electron or donate that electron to neighboring molecules. Can you visualize that? So free radicals have unpaired electron. Because they have an unpaired electron, they are unstable. To stabilize it, they either lose the unpaired electron or grab an electron from nearby molecules. Okay? Now they have a very short life, only about 9 to 12 seconds. Very, very short. Before they collide with another molecule, that's what I said, either abstract or donate the electron to achieve stability. Abstract, this is a verb. This is different from an abstract, which is a noun. Abstract means to take or grab. So, as I've said before, the free radicals either take an electron from a molecule or donate that electron to the molecule. Okay? So what happened? If it donates an electron to a stable compound molecule, that stable molecule becomes unstable because it has the unpaired electron. Okay? Now, if they remove an electron from a molecule, that molecule will now have an unpaired electron. So it also becomes a free radical. So it is self-perpetuating chain reaction, producing free radicals. Now, what happens if two free radicals collide with each other? Well, each one of them has an unpaired electron, then they become stabilized. Okay? So it terminates the chain reaction. So it says here, a free radical can be quenched, so terminating this chain reaction if two radicals react together. So when two unpaired electrons now become paired, nagpares na in one or other of the parent molecules. Now it says here, this is a rare occasion. No? This is a rare occurrence because free radicals have a very short half-life and very low concentration in the tissues. Very low concentration in the tissues. Okay. Very low concentration. However, if they remain free radicals, they can do damage by the chain reaction. All right. The most damaging species is your superoxide. You see this dot here? That is a sign of a free radical. This is an oxygen O2 with a dot as a superoxide. A hydroxyl, there's the dot, and then an OH. Per hydroxyl, we have a dot here, O2H. Okay. Tissue damage caused by oxygen radical is often called oxidative damage. And compounds or molecules that prevent this are known as antioxidants. Okay? Alright. Radicals can damage DNA, lipids, and proteins, that as we mentioned earlier. Okay. Interaction of radicals with bases. The bases in your DNA or RNA or nucleic acids, it's either a purine or pyrimidine. It's two bases. Your purines, there are two, adenine and guanine, and pyrimidines, you have cytosine, uracil, and thymine. Okay. So interaction with the bases. So interact with the purines or pyrimidines that lead to chemical changes, and if not repaired, can be transmitted to a daughter DNA. When a cell subdivides, it now have a damaged DNA in both of the daughter cells. No? So that is how mutations can come around. All right. It says it can also damage lipids. The usual lipid is fatty acids. And you know there are two kinds of fatty acids, saturated and unsaturated fatty acids. It is usually the unsaturated fatty acid that is attacked by the free radicals. Okay. The plasma lipoprotein also contains fatty acids. And usually, fatty acids are also found in your lipoproteins. No? So this can be attacked. So peroxides can be formed if the double bond is being attacked by the free radicals. And you will have a lipid peroxides. Then it becomes a dialdehyde. And a dialdehyde can affect your nucleic acid and can also modify proteins. Proteins are also subjected to direct chemical modification by free radicals. Now, the OH in your tyrosine no, can lead to the formation of dihydroxyphenylalanine that can undergo non-enzymic, no enzymes involved, leading to further formation of oxygen free radicals. The oxygen free radicals are usually known as ROS or reactive oxygen species. Reactive oxygen species. All right. It says here formation figure 41-1 or 45-1. Here we are. You have your fatty acids here, a double layer, double lipid layer. Okay. Now, a macrophage engulfs an LDL. And this LDL is affected by free radical damage. Okay. And this LDL can no longer be recognized by uh, organs that has receptors for LDL because this has been changed. It has been oxidized. And as a result, it cannot be taken in by cells that, or let's say organs that take in LDL. Like for example, LDL receptors in the liver. So they cannot be taken in by the liver anymore. Huh? Okay. Now, as a result, it forms dialdehyde. That aldehyde can affect your proteins, the amino acids here, on your integral protein of your lipid bilayer. Okay. So this is peroxidation of lipids in the membranes. And it forms dialdehyde. The dialdehyde, similar to that one, can also affect your nucleic acid, specifically your DNA. That's your DNA here. Okay? So radical damage will lead to mutations, cancer, autoimmune disease, and atherosclerosis. Okay, radical damage to the DNA will affect, of course, the germline. On the germline cells of the ovaries, okay, that's the egg cell, and the testes, and that's the sperm cell, and can lead to heritable mutations of somatic cells and result to cancer. The dialdehydes formed as a result of radical induced lipid peroxidation in cell membranes can also modify the bases, purine and pyrimidines in DNA. Okay. What about the amino acids? The amino acids and proteins can either be acted upon directly by the free radicals, and as a result, you have radical induced, as a result of reaction with the products of radical induced lipid peroxidation, and leads to a protein that are recognized as non-self. What happened to this here? Non-self, meaning the immune system will now act on it because it is non-self. It is not a normal protein. So the immune system, recognizing it is non-self, attacks on it, and we have what we call autoimmune diseases as a result of that. Autoimmune diseases. Meaning to say that in your immune bodies are turning against your own cells because they were recognized as non-self because they had been altered by the free radicals. All right. Now here we have here chemical modification of proteins and lipid of your LDL. No? Leads to abnormal in LDL and no longer recognized by the liver. The receptor of LDL does not recognize the abnormal LDL anymore. So it cannot be taken in by the liver. So it is not being cleared by the liver. The macrophages now take them up. As you know, your macrophage are scavenger. So these are oxidized, the LDL here are oxidized lipids already. So the lipid engorged macrophages infiltrate. Okay, infiltrate. That means it attacks the tissue, infiltrate under the blood vessel endothelium. The blood vessel endothelium, or the inner wall of your blood vessel, is very, very smooth. Teflon smooth. You know what's Teflon, no? Teflon smooth. Okay. Now, this is invaded by these macrophages, which contains LDL. And LDL is the carrier of cholesterol. And that cholesterol should have been brought to the liver to be metabolized. However, because the receptors cannot recognize anymore the oxidized LDL, then it is not taken up by the liver. Macrophages will remove them. No? And the macrophages infiltrate together with the damaged LDL inside it, infiltrate the blood vessel epithelium. Okay. Especially if there is already some cracks in the endothelium. So how are these cracks usually formed? In the endothelium of the blood vessel, as we said that the blood vessel, the inside, the intima, is very, very smooth. Now, the idea that it should be smooth is that the what you call this, the foreign elements of your blood will have a smooth sealing when they pass inside the blood vessel. No? All right. It should be very, very smooth. Now, sometimes there is some already a little damage or cracks in the intima. What brings about this? Now, you should remember that the blood vessel is made up of one of the protein that is very, very important protein. In fact, this protein is found in large amount in the body because all cells, almost all tissues, contains this particular protein. And this particular protein I'm talking about is collagen. Okay? Now, these collagen are plentiful in the blood vessel wall. Plentiful in the blood vessel wall. Okay. And this, of course, is very, very important because collagen is quite a strong protein. It is made up of a triple helix. A triple helix. So you can see how it is, no? It is not only a singular helix, but a triple helix, the fibers of this protein. Now, if this is weakened, then as a result, this weakened, cracks may be seen. Now, this is due to what we call inability of the collagen fibers to have hydrogen bonding of the triple helix. There's not so much hydrogen bonding. The hydrogen bonding is contributed by two amino acids that has been modified. This is your lysine and your proline. This is hydroxylysine and hydroxyproline. Now this amino acid is hydroxylated through an enzyme hydroxylase. And this hydroxylase is dependent on a very important vitamin, and that is vitamin C, ascorbic acid. Without vitamin C, hydroxylation cannot occur because these hydroxylases, the enzymes, are dependent on vitamin C. Okay? And you know what is the result of a deficiency in vitamin C? You call it scurvy. So you can say that when there are cracks inside your blood vessel wall, it means that the hydroxylation is not as it should be. So that means the collagen is weak. Now, why should there be damage? You should remember that your blood vessel is your arteries are subject to constant pressure, always constant pressure. As long as you are alive, they are almost always under pressure because every time the heart pumps, that's a pressure. And how many times does the heart beat every day? And that's about 100,000 beats. So imagine that your blood vessel is pulsating 100,000 times a day. 100,000 times a day. And there is a watery liquid, and that is your blood, inside it. Oh. So it's pulsating. It is relaxing, contracting, relaxing, contracting, relaxing, contracting. Because that is how it is. It is for pushing the blood every time the heart beats. Okay, so it's pulsation. That's the one that you look for in the pulse. Oh? Okay. So, as a result of that, those cracks are usually being smoothed out. This is smoothed out by oxidized macrophages containing your oxidized LDL. And what does it contain? Cholesterol. And you know cholesterol is smooth. So it's smoothed out, yes, cover the cracks. But then, cholesterol is sticky. So as a result, your form elements of the blood, RBC, WBC, no, will stick to it. So as they stick there, the intima becomes rough again. So another layer to smooth it out, utilizing oxidized LDL from the macrophages. And so that area grows. And you have now what we call atherosclerotic plaque. And sometimes the plaque is so big already that it can even occlude the blood vessel. Okay? Understand that? All right. Now, a very important component of the blood, aside from WBC, RBC, other form element, is the platelet. This platelet, once it runs over a rough surface, it bursts. And once it bursts, it initiates right away the clotting mechanism. And we cannot afford to have a blood clot in our blood vessel because the blood cannot pass through anymore. And if this happens in very, very small blood vessels in your brain or other organs or in your heart, no? So it occludes or plugs the flow of blood. And certain areas of the tissues cannot be supplied anymore by blood. And you have a stroke. So you have a heart stroke, you have a brain stroke. Okay? All right, so let's continue. There are multiple sources of oxygen radicals in the body. Okay? Ionizing radiation, X-rays, and UV rays analyze water, leading to the formation of hydroxyl radicals. Now, what other radiations are you subjected to? Aside from X-rays and UV rays. Have you ever heard of radiation from your computers? Radiation from your cell phones? Or radiation from high tension wires? High tension wires.
Doc.
High tension wires. Now, about the internet. Your cell phone now is 4G. Diba? And now some scientists are concerned about this 5G. Okay, 5G. Another is in your kitchen, microwave oven. Huh? Microwave oven.
Doc,
Right.
excuse me, Doc.
Yes.
How harmful is the radiation from the microwave, Doc?
Well, it is not harmful if you are not within the range. So if you are just 1 meter away from your microwave oven, that's okay. Just like your television, you must be at least 1 meter away. That's safe enough. What about your cell phones? Okay. Your cell phone is harmful when it is right against your body. But the radiation is very, very small. But accumulation, so it's much better to carry your cell phones in a bag. Okay? Now, we still don't know what is the effect of this 5G. All right. So we have ionizing radiation, X-rays, UVs, analyze water, leading to the formation of hydroxyl radicals. Transition metals, including copper, cobalt, nickel, and iron, can react without the use of enzymes. they can react with oxygen or hydrogen peroxide, again leading to the formation of hydroxyl radicals. All right. But these metals are very, very important in our body. Like, for example, iron. You need that in your hemoglobin. Now, nature has it that these metals are liganded or are liganded to proteins, and so makes these metals inactive. Unless they are released from the protein where they are bound to, then they can be reactive with oxygen. You know, your copper, ceruloplasmin, di ba? Iron, your hemoglobin and myoglobin. All right. Now, another important compound is nitric oxide, NO. NO is a vasodilator. Vasodilator. This is synthesized from the amino acid arginine through your NO synthase or nitric oxide synthase. And it is also very important in cell signaling. This is one way where cells communicate with each other. You know, the cells are also communicating with each other, just like us. We communicate with each other, or you can say that the cells are also chismoso or chismosa, diba? Through nitric oxide. Nitric oxide was first originally, as an endothelium-derived relaxation factor. So which means it relaxes the endothelium. And where is the endothelium? That's in your blood vessel. It relaxes your blood vessel. Nitric oxide. Very, very important compound. And also a very important compound for the males or even the females. Because nitric oxide can open up blood vessels. And why in the males? Well, you should remember that erection does not occur unless the blood vessels in the penile tissue are enlarged, and so that blood can get in. And that is the work of nitric oxide. And that is how Pfizer becomes richer, because of the discovery of sildenafil. You know what is sildenafil? Anyone knows?
Viagra.
Oh, Ramadana. That's your Viagra. Sildenafil. You know, Pfizer was researching on how to be able to get a compound that relaxes the blood vessel. They are for us against hypertension. And they accidentally made a compound, sildenafil, which increases the production of nitric oxide. And it is quite specific because it increases the nitric oxide in the penile tissue. As well as in the clitoral tissue. So it's not only men that uses Viagra. Women can also use it. Okay. So, but this nitric oxide is a free radical, and it can react with superoxide to yield peroxynitrate, which grades itself to form hydroxyl radicals. See?
Yo, makaduwak mo. So, ganyan ka.
Here you are.
Hindi lagi. Is year, 1 year, 1 year interval.
Here your
Pakana ba ako ano to? Sa, wala, ito
ayaw
sa kinapot ka itong ano, sinuwilit, may kapag sinuwilit.
is
Wala nagyo ka na, tasik sugar. Uy, direct.
it is depicted as a lightning, ionizing radiation. It affects your lipid bilayer. Okay. All right. There you are. Nitric oxide synthase, from integral proteins of your bilayer. You have arginine and can release nitric oxide. Okay, it's a radical itself, but this radical is used as a cell signaling, signal from each other, and it also relaxes the endothelium of the blood vessel, so that the blood vessel increases its caliber, so that blood can pass. Okay. Now, what do you mean by respiratory burst of macrophages? So it is a respiratory burst of activated macrophages. See chapter 53. All right. And it has to do with the formation of NADPH. Now this compound, NADPH, is a product of the oxidation of glucose without forming ATP. And they call this the hexose monophosphate shunt or pentose phosphate pathway. Pentose phosphate pathway. And there are two products of this pathway out of glucose: NADPH and ribose 5-phosphate. NADPH is a reductant, very important. It's a reductant. And the other product is ribose 5-phosphate, which is needed in the formation of purines and pyrimidines. And you know where your purines and pyrimidines are going to be used in the formation of your nucleic acids. Now sometimes I call this pentose phosphate pathway or hexose monophosphate shunt as a pathway for growth. So, but it also is important in free radical emission. As a result of this, when you have plenty of NADPH here, and this is the reaction, NADPH reduces your oxygen not into water, but superoxide radical and protons. And you have now an oxidized NADP. Now I say that NADPH is needed for growth because NADPH is used in synthesizing bigger molecules out of small molecules. So the small molecules, like for example, how do you form fats? It's made up of, or your fatty acids are made up of acetyl-CoA, 2 carbon atoms, and they are put together, and it requires NADPH. So our body can synthesize fatty acids 2 carbons at a time. So there is always an additional of 2 carbons, and that 2 carbons come from acetyl-CoA. All right. So there you are. NADPH is a reductant. It reduces oxygen. Now, instead of forming water, it forms superoxides and protons. Okay? And this is brought about by this enzyme, NADPH oxidase. All right. There are various mechanisms of protection against radical damage. First, metal ions undergo, again, non-enzymic reaction. Metal ions that undergo non-enzymic reaction to form oxygen radicals. Remember, as I said, the ions, the metals that we have in the body are bound to proteins, transport protein or storage protein for the metals, no? And they are non-reactive, meaning no oxidation can occur. However, when they are free from the protein that they are bound to, they can now react, no? And can form oxygen radicals. So it says here, non-normally free in solution, but are bound either to proteins from which they provide prosthetic group. Prosthetic meaning non-protein group, or like him, no? Yeah, iron is bound to transferrin, ferritin, okay, and hemosiderin. I'm going. Where is this? Copper to ceruloplasmin and other metals to metallothionein and their protein. They are transport proteins and they are too large to be filtered in the kidney so that they are not lost in the urine. Superoxide is produced both accidentally, and as the reactive oxygen species required for enzyme catalyzed reactions. Not all of the catalyzed reactions, no. Enzymes that destroys the superoxides, known as superoxide dismutase. And these superoxide dismutase are found all over your body. I mean, in all other tissues, no, in most tissues. So where is the superoxide? Auto with a negative sign, okay, and form hydrogen peroxide. Although this is also a radical, this is much less potent as your superoxide radical. Now this hydrogen peroxide will now be acted upon by two other enzymes, catalases and peroxidases. Okay. All right, so we have here catalase and peroxidase. And the reaction is this one. Hydrogen peroxide forms into water and oxygen. Okay. Through the effort of this catalase and peroxidase. Okay. So superoxide dismutase, catalases and peroxidases acts on this very, very potent superoxide radical. Now, the combination of vitamin E and vitamin C are seen as a tandem to remove free radicals. Example. Okay. We have two enzymes here, vitamins here. This is your vitamin C, tocopherol. Vitamin E, I'm sorry, vitamin E. And this is your vitamin C, ascorbic acid. Okay, you have here this vitamin E acts on a medium where it is fatty, oily, or greasy, meaning fatty acids, cholesterol, and all those that belongs to the lipid family. While your vitamin C acts on aqueous solution, no? Because this is water soluble. This vitamin C is not effective in a lipid medium, nor vitamin A is effective in aqueous solution or aqueous medium. Okay, so let's look at this. Now, tocopherol, when it is trying to stop the function of a free radical, they become a free radical also. So there is lipid peroxide. So the lipid peroxide that has been damaged by a free radical now becomes a hydroxy fatty acid. No more free radical. But the free radical now is transferred to your alpha tocopherol. Here it is. Here. All right. As a result, you will have now three kinds of tocopherol radical. This one, and this one. No? All right. This free radical now interacts with ascorbic acid. Okay? The ascorbic acid removes this free radical on your alpha tocopherol. And so it becomes, again, tocopherol, and your ascorbic acid becomes already having the radical itself. It is monodihydroascorbic acid. Monodihydroascorbate. So that. So they usually work in tandem, vitamin E and vitamin C. Okay. So they act together, no? From a lipid environment to an aqueous environment. Ascorbic acid, uric acid, and polyphenols coming from plant foods act as water-soluble radical trapping antioxidants. So it traps the free radical, forming a stable radical that persists long enough to undergo reaction to non-radical products. Okay. Ubiquinone and carotenes similarly act as lipid-soluble radical trapping antioxidants in membranes and plasma lipoproteins. So lipid-soluble, no? So you have ubiquinone and carotenoids, which of course becomes vitamin A. Vitamin A. Now here is the paradox. That I mentioned earlier kanina, di ba? Sabi na an increase of vitamin E and vitamin C can bring about cannot really affect so much when you have so much already of this. Now it says here, vitamin C is easier because we need only about 100 to 120 milligrams per day. And if you take in more than that, it is excreted in the urine. Excreted in the urine. Okay, so it's not a big problem. But the big problem is your vitamin A. Although ascorbate is an antioxidant reacting with superoxide and hydroxyl to yield monodihydroascorbate and nitrogen peroxide or water, it can also be a source of superoxide radicals by reacting with oxygen and hydroxyl radicals, and by reaction with copper ions. See, this is free copper. However, these pro-oxidant actions require relatively high concentration of ascorbic acid, which are unlikely to be reached because we only need this one, and the rest are easily excreted in the urine. Okay. So here's the one here, antioxidant and pro-oxidant roles of your vitamin C. Okay, this is superoxide radical, form hydrogen peroxide, and ascorbic acid becomes monodehydroascorbate. Catalase and peroxidase catalyzes hydrogen peroxide to water and oxygen. Ascorbic acid with a hydroxyl radical forms water and monodehydroascorbate. That's the antioxidant role. Pro-oxidant roles, ascorbic acid plus oxygen, you form superoxide radical as monodehydroascorbate. Ascorbate with free copper, you form now a hydroxyl radical. Copper and hydrogen peroxide. This copper is cuprous. This one is cupric. Forms cuprous as hydrogen peroxide. It forms now hydroxyl radical. Okay, so that is, but it did not say that if you are low on vitamin C, then this cannot occur even if you are going to increase your dosage of vitamin C intake. If this is low, you are in a pre-scorbutic, meaning very low vitamin C or absent. But you cannot see this scurvy anymore, frank scurvy, because people are already vigilant. The free scurvy before was only seen by the seafarers, not our modern seafarers. The seafarers before that crossed the ocean for so many months. Why? Because they do not know about this vitamin C yet. This was the time of Magellan, where they crossed the ocean several months. And what is their provision? Their provision does not have food with vitamin C. What they usually have is cereals or grains and preserved meat. And the preserved meat is preserved with salt. And there is no plant food, fresh plant food like vegetables, because they do not have refrigerators at that time or coolers. So they cannot stock fresh vegetables, which is the source of vitamin C. So that's why the sailors before are prone to have scurvy. And the British called their sailors before limies. Why should they call them limies? Limies is Lemies. Or there is only one M. Basta limis. And that word comes from lemon. Because every time they sail out, they bring with them a sack of lemons. A sack of lemons. And that is the one that gives them vitamin C. during their travel. Okay? So, Americans, you call them GI Joes, or there's another term for sailors. But the British, they call them limies. All right. Now here is nitric oxide. And other radicals are important in cell signaling, especially for, so there's another function of nitric oxide aside from it is a vasodilator. It is important for programmed cell death, apoptosis. Now, when a cell has damage already, especially if the damage is on the DNA, they are usually now being tagged to be destroyed or degraded. And nitric oxide is very, very important in this because they tag cells that are to be destroyed. Apoptosis. Okay. That have suffered DNA and other damages. It is likely that high concentration of antioxidants so far from protecting against tissue damage may quench the signaling radical. And we remember we said nitric oxide is a radical. So if we are going to destroy all the free radicals in our body, quench the signaling radicals. So it cannot, your nitric oxide, which is destroyed by antioxidants, then it cannot tag cells that are to be destroyed for what they call programmed cell death or apoptosis. And so it permits the continued survival of damaged cells, increasing rather than decreasing the risk of cancer development. Because cells that are programmed to die or to be destroyed usually have damaged DNA. And damaged DNA always produce mutations. Okay? That's your free radicals. The next one, metabolism of Sinobiotics, Sinobacilla. There's another word for that, Sinobiotics. This one is XENO. But another is Sinobiotics, SINO, biotics. That means biotics coming from China. And that's why they call their vaccine Sinovac, Chinese vaccine. No? Okay. Importance. All right, Sinobiotics. Sino meaning sinos in Greek or foreign. Anything that is foreign in the body that you introduce, anything. No? So this includes medicines, food additives, environmental pollutants. Environmental pollutants, whether we eat it or we inhale it. Or we can also consider sound as a pollutant. No? All right. We encounter many Sinobiotics that must be metabolized before being excreted. Okay. Drugs are considered Sinobiotics. I've always said before, either this drug is legal or illegal. Then you have chemical carcinogens or compounds in plant foods, and a wide variety of compounds that have found their way into our environment, like PCBs, biphenyls, these biphenyls, and insecticide, and other pesticides. Now, you find this in your plastics. A lot of marine animals now have died because of plastics. Because of plastics that goes into the sea. And degradation there is very, very slow. Sometimes they are eaten as a whole, or sometimes very small particles of plastics are eaten by small fish. And since that cannot be metabolized, they stay in their tissues. And these small fish are eaten by big fish. The big fish now eats also the plastics that these small fish have been eating. And of course, this can be a hindrance to their metabolic processes. So we can just can say that in the long run, if plastics will be around with us and it usually goes into the sea, we may lose all our marine life, in which a large number of people are dependent on marine food. Okay. Aside from that, the usual ones that we take in are these chemical carcinogens that are added into our food, and insecticides that we inhale, pesticides, all of that. And your main organ for metabolism of these Sinobiotics is the liver. Now, in the liver, a Sinobiotic is being handled by making these compounds water soluble. And if they are water soluble already, they can be excreted in the urine. So there are two phases in the liver, phase 1, phase 2, for making this compound water soluble. So we call them phase 1 reactions of the liver and phase 2 reactions. The phase 1 reaction is hydroxylation of these Sinobiotics. So you know hydroxylation, putting an OH. All right. Putting an OH into a compound does not necessarily mean that you have already removed the potency of that compound. Sometimes hydroxylation reactions may make the compound more potent or more toxic. That's why there is the need for a phase 2 reaction. The phase 2 reaction adds compounds to the xenobiotic so that the xenobiotic becomes now or rendered less toxic or non-toxic and is water soluble and excreted through the urine or through your kidneys. No? Okay, here we are. Two phases, phase 1 reaction. Okay, phase 1 reaction. You have a group of enzymes. This one, Cytochrome P450. This is quite a versatile enzyme in the sense that it does not only perform hydroxylation reaction or putting an OH, but they can do all the reaction like deamination, removal of amino group, dehalogenation, removal of a halogen. You know what are halogens, diba? Bromine, chlorine, fluorine. Okay. And desulfuration over of a sulfur, epoxidation, peroxygenation, and reduction reaction. You see? The enzymes that we mostly know is usually perform only one type of reaction. And sometimes some enzymes are very, very specific only for one substrate. But this cytochrome P450 is very versatile. We mentioned already this deamination, the halogenation, the sulfuration, etc., aside from hydroxylation reaction. Okay. Cytochrome P450. The cytochrome P450, there are about, so far, they have seen is 57 of them. 57 cytochrome P450. All right. So that's phase 1 reaction. So let's look at phase 1. The main reaction involved in phase 1 is hydroxylation, brought about by a family of enzymes known as monooxygenases, meaning they add an oxygen. No, mono, only one. Okay? They are also called cytochrome P450. And there are 57 cytochrome P450 genes that they have seen in the human genome. Cytochrome P450, just like the other cytochromes that we mentioned in your respiratory chain, is a heme enzyme. Why 450? Because when it was discovered, it was having an absorption peak of 450. Okay. So they prepared a microsome from the endoplasmic reticulum, chemically reduced, then exposed to carbon monoxide, and had an absorption peak of 450 nanometers. That's why they are called Cytochrome P450. At least half of the common drugs that we ingest are metabolized by isoforms of Cytochrome P450. What do you mean by isozymes? What do you mean by that? Isozymes are enzymes that catalyze the same reactions, but they are not the same in structure, and components. Okay. Isoforms of cytochrome A450, they also act on steroid hormones, carcinogens, and pollutants. In addition, cytochrome P450 in the metabolism of physiological compounds, for example, synthesis of steroid hormones, and the conversion of vitamin D to its active metabolite, calcitriol. All right, so that's phase one. Oh, wapa, moment. So this is the overall reaction catalyzed by cytochrome 450. You have a compound, reduced compound. You have an oxygen, and again NADPH. And then the compound becomes hydroxylated. Okay, so if this is your synobiotic, that synobiotic now is hydroxylated, and you form molecule of water and the oxidized form of NADPH, NADP. So you can see this reaction in chapter 12, figure 12-6. Cytochrome P450 reductase. Okay. Another one, cytochrome B5, another hemoprotein found in membranes of smooth endoplasmic reticulum, is involved in electron donor in some cases. Okay, let's look at our, okay. So we have isoforms of cytochrome P450 from a superfamily of heme-containing enzymes. There is a systematic nomenclature. So the root name is CYP. This followed by a number of designating the family. Cytochrome are included in the same family if they exhibit 40% of amino acids. It is followed by a capital letter indicating the subfamily. Okay. And are the same if they exhibit more than 55% sequence identity, meaning the amino acids are more or less similar, 55% sequence identity. The individual 450s are then assigned numbers in their subfamily. Okay, so here we are, cytochrome, okay, it's the first, and then subfamily A, and the first of the subfamily A. Cytochromes are found in the liver cells and enterocytes. What do you find enterocytes? The word entero meaning intestine. Okay. So you know where they are now. And then,
Heart
remember,
engineers.
okay, both,
But this is what you can call me Greg.
okay.
Are you already aware for what I have what?
Okay, overlapping specificity of cytochrome P450 explains interactions between drugs, between drugs and nutrients, no? Okay. Most cytochrome P450 are inducible, meaning this can increase if you give a compound that induces its formation. So they are inducible. Okay, an example, phenobarbital can increase the formation of cytochrome B450 within a few days. In most cases, involves an increased transcription to messenger RNA. So this is in the endoplasmic reticulum. No? So there is a threefold increase cytochrome P50 if you give phenobarbital. All right. Now this usually brings about drug interaction. No? Like for example, a patient is taking blood coagulant, coumadin sodium, coumarin or coumadin sodium. Another name is warfarin. And this coumadin sodium or warfarin is used in or are components of a rat poison. That's the common rat poison that you know. Dora, no? Dora. It contains warfarin. It's a blood anticoagulant, or meaning blood thinner. So blood thinner makes your viscous blood thin out. That's warfarin or coumadin sodium. You use that for poisoning rats. Now, usually when you do not use warfarin, you poison a rat with another poison, and you know rats goes into a hole. And if they die in the hole, then it smells, no? And you do not know where it is. With coumadin sodium, or this warfarin, the rats who take this will go into hemorrhage, internal hemorrhage. And when an animal is in hemorrhage, there is always that feeling of thirst. So the rat comes out of the hole from where they come from, and then they drink water. They drink a lot of water, and they die. So they die outside of the hole where they are staying. You see? That's your warfarin. Okay. So this warfarin is also used in blood thinning of a person, especially if it is hypertensive and the blood is viscous. So you usually give a blood thinner. No, because a very potent blood thinner is coumadin sodium. Now, there is a less potent blood thinner, and that is your common aspirin. The common aspirin, that's a blood thinner. Okay, so what has this got to do with the interaction with Cytochrome P450? And it says here, phenobarbital, when given, will induce the formation of Cytochrome P450. Okay? Now, if you have a patient who is on warfarin or blood thinner, okay, and then he needs to be given phenobarbital, needs a barbiturate. Naturally, Cytochrome P450 will act right away on, because it is induced by phenobarbital, your warfarin will be destroyed right away. So what do? You increase the dosage of warfarin to be effective. Diba? And then, especially if this is in the hospital setting, it says, there is no need for phenobarb for this, so you withdraw the phenobarb. But you did not decrease the dosage of your warfarin or your coumadin sodium. So what happens? The patient goes into hemorrhage, bleeding tendencies. So that's one of the interactions. Okay. All right, so you have it there. Induction of cytochrome B5 underlies drug interactions when the effects of one is altered by the administration of other. Anticoagulant warfarin is metabolized by cytochrome 2C9, cytochrome P50. This is a family of cytochrome 450, which is induced by phenobarb, will increase the metabolism of warfarin, so reducing its efficacy, so that the dose must be increased. The metabolism of some widely used solvents and compounds, also like tobacco smoke, many of which are pro-carcinogen. It is induced by ethanol, so increasing the risk of carcinogenicity. That's another. Or naturally occurring compounds found in food, in fruits, like grapefruit has furanocoumarins, that is a blood thinner, which inhibits cytochrome 450 and so affect the metabolism of many drugs. Some drugs are activated by cytochrome 450, so that grapefruit will reduce their activity and are inactivated by cytochrome 450, so that grapefruit increases their activity. Drugs that are affected include statins, omeprazole, antihistamines, and benzodiazepine antidepressants. So be careful with these drugs. Polymorphism of Cytochrome P450. This, of course, very low metabolism of nicotine to conitin. Cytochrome 2A6 have been identified a wild type and two inactive alleles. Individuals with the non-alleles of impaired metabolism of nicotine are apparently protected against becoming dependent on tobacco. These individuals smoke less, presumably because their blood and brain concentrations of nicotine remain elevated longer than those of the individual. So there is no craving for nicotine. So there is no need to smoke. So they smoke lesser. No? Okay. All right. That's phase one. Phase two reaction, after the synobiotic is hydroxylated, they are made more soluble in water by adding glucuronic acid, sulfate, or glutathione. And this is conjugation reaction in phase two. So 5 types of phase two reactions. One is, naglaw-coronidation man eh. That is glucuronic acid, glucuronidation. The wrong spelling. So addition of glucuronic acid. Second one, addition of a sulfate. Third one, conjugation with glutathione. And this is the most important thing for your glutathione to work in your body. Glutathione, conjugation of glutathione. And then it is acetylated, and then it is methylated. And so that makes the hydroxylated synobiotics in phase one more soluble in water and can be excreted through the kidneys and into the urine. Okay? First reaction is glucuronidation. It's the most frequent conjugation reaction. So glucuronic acid. Where would we get glucuronic acid? We get glucuronic acid from the oxidation of glucose in what you call your uronic acid pathway. Uronic acid pathway, which produces glucuronic acid. Okay. This is also used to make your bilirubin soluble in water. Glucuronic acid to your bilirubin. Medtics are familiar with this. They say when only one glucuronic acid added to bilirubin, you call it bilirubin monoglucuronide. And then if 2 glucuronic acid added to bilirubin, it becomes bilirubin diglucuronide. And they do test for this, diba? Okay. So UDP glucuronic acid catalyzed by glucuronosyl transferase, an enzyme that transfers glucuronic acid. And they are present in the endoplasmic reticulum and the cytosol. Molecules as 2-acetyl-aminofluorine, a carcinogen, aniline, benzoic acid, miprovamate, a tranquilizer, phenol, and many steroid hormones are excreted as derivatives of glucuronic acid or glucuronides. The glucuronide may be attached to the oxygen, nitrogen, or sulfur groups of the Sinobiotics, the substrate. Okay? That's number one, conjugation reaction. Number two, sulfation reaction. Some alcohols, arylamines, and phenols are sulfated. So you know that already. Sulfation reaction. Steroids, glycosaminoglycans, glycolipids, glycoproteins, no, is the active sulfate. The donor of that is SAM, SEM. Ano? Active sulfate, I'm sorry. It's not SAM, it is PAPS. Phosphoadenosyl phosphosulfate. Phosphoadenosyl phosphosulfate, or also known as adenosine 3' phosphate 5' phosphosulfate. But they usually call it PAPS, phosphoadenosyl phosphosulfate. Okay? Conjugation with glutathione, all electrophilic compounds. The tripeptide glutathione, made up of glutamic acid, cysteine, and glycine. Very important in fish to metabolism. Okay, so here is your synobiotic. This is your glutathione. And so your synobiotic now has this. That's a sulfur there. R is the electrophilic compound, 4 classes of the cytosolic glutathione transferase. Transfers that glutathione to the compound, synobiotic. This is an electrophilic compound. Okay. Then you have two others, acetylation and methylation. So an acetyl group is added to the synobiotics, and now the synobiotics has the acetyl group. It is acetylated. Some synobiotics subjected to methylation. Now instead of acetyl group, a methyl group is added. And the enzyme is methyl transferase. The enzyme here is acetyl transferase. So this is S-adenosyl methionine. This is your SAM, S-adenosyl methionine, as your methyl donor. Methyl donor. The methyl group of methionine is used. Responses to synobiotics include toxic, immunological, and carcinogenic effects. Okay. So this is binding to your DNA and RNA and the protein. cell injury known as cytotoxicity. So the synobiotic binds to DNA, RNA, or a protein, which is really toxic, resulting in cell death or antigenicity, acting on a protein, bind to a protein acting as a aptin, altering its antigenicity. Also, this is a toxic, immunologic, and result autoimmune disease. Then carcinogenesis. Epoxide becomes dihydrodione. Oh. Are you still there?
Yes, Doc.
Yes, Doc.
Yes, Doc.
Yes, Doc.
Okay.
Yes, Doc.
So tomorrow, no class.
Yes, Doc.
And maybe Monday, next Monday, Dr. Barito will be your teacher, and she will have plasma proteins and immunoglobulins. And I think it's Monday, no? So, plasma protein and immunoglobulins. Dr. Barito. I do not know, I am not sure yet whether it's Monday or Tuesday. So if it is not Monday, if she will not be lecturing on Monday, I will be lecturing on Monday. Okay? If she lectures you on Monday, I'll be lecturing on Tuesday. And my topic would be muscle and cytoskeleton. Okay?
Hi, Doc.
All right. So let's end the day.
Yay.
Thank you, Doc.
Okay.
Thank you, Doc.
Thank you, Doc.